Good morning, everyone. Today I'll be presenting AudioGap, a new research project that uncovers a cover channel in AirGapped systems by exploiting EM leakage from audio ACs. This work was conducted by us, a group of researchers from IETR laboratory from Rennes City in France. First of all, air-gapped systems are physically isolated from external networks, which means that from the system to the outside world, there is no physical communications, no Wi-Fi, no Bluetooth, no Ethernet, no cables, making them the golden standard for high security environments. However, they are not impervious to attacks. Electronic devices naturally emit EM signals, which can be weaponized to breach this isolation. This hidden risk forms the basis of our cover channel attack. Attackers can exploit these EM emissions by infecting the system with malware, which we call the Trojan, that manipulates hardware to encode data outside the air-gapped system. Traditionally, the cover communication in air-gapped systems heavily relies on binary encoding. This is due to the complexity of attacks to exfiltrate data from such a high securely environment. Think about this as an EM communication channel, a radio communication channel. Well, the air gap itself, the targeted chip in the air gap is the antenna. The Trojan is the transmitter that encodes data transmitted through EM waves. Well, while the attacker at some distance, the range, it installs the antenna and receives and decodes the exfiltrated data. Existing research lacks guidance on discovering new vulnerabilities or analyzing signal characteristics. We don't know exactly how to find the new vulnerabilities. We don't have protocols to find any new vulnerabilities. The only papers in literature says that this chip present a vulnerability, and we can implement the attack using this method. But we have no insight to find the new ones. Now, if we point to some chip, the emitted signal or the leakage, we don't know exactly what is the form of the signal, and we don't know the location of the signal in the frequency domain, because the location is the receiving frequency from the attacker side. So we don't know the form to do the modulation, and we don't know the position to receive the signal. State-of-the-art approaches actually focuses more on surpassing the binary transmission barrier, and they achieve this through modulation, signal modulation, just like data modulation in classical communication channel. And they achieve the modulation by fine controlling the targeted chip to mimic local oscillator behavior to the chip signal, to the chip signal. So our perspective is that why we bother with fine control if we can use the oscillators existed in the system itself, and those oscillators integrated are the clocks. Here we can notice what we call an automodulation phenomena. Automodulation is a natural, which means that the attacker does not have any intervention to create it, a nonlinear coupling between a carrier and the subcarrier signal in nearby components. So the carrier, it is the local oscillator, and we say it is clock. So clock has a square wave. Square wave has its components, harmonical components are purely odd components. But however, because the noise interference, the jitter, we can see also the existence of the even harmonics, making that the carrier has an even and odd harmonic composition in frequency domain. The subcarrier is the leakage of digital signal, which make it also square wave, but with non-constant period, like the clock. And so it will also present odd and even harmonics because it is deformed square wave. And the mixing or the nonlinear coupling gives the harmonics of the clock, the blue ones, AM, amplitude modulate the subcarrier or the digital signal digital signal harmonics, and creating a harmonic AM modulation of harmonic. We can modulate this using SSAM equation, which is System Signal Auto Modulation for SSAM. And because we speak about AM modulation, amplitude modulation, then in frequency domain we can use the convolution, because in AM modulation, in frequency domain it is a convolution, and in time domain it is a multiplication. If we develop the SSAM equation, we can find the infinite sum that says that the SDS, which is the information, SDS that represents the information or the digital signal or the subcarrier, is present at every integer harmonic of the local oscillator or the clock. Now back to the audio IC, because the audio IC has a master clock and an ADC. So the master clock is the local oscillator, the ADC is the digital signal. The ADC is the analog to digital converter that samples the audio signal. Then, because it samples it, it creates a numerical signal, which are the bits, and those bits are the subcarrier signal. So if we change the parameters of the audio sampling, which are the sampling rate and the bit depth, then I can change the SDC signal, and I can change the period of the composition of the subcarrier signal, the square wave, and thus this is reflected as the unique harmonic pattern. This unique harmonic signature can be presented by the frequencies, the harmonics, and their peak points. For example, P1 is the first harmonic, P2 is the second harmonic, and so on and so forth. And for the software, from software side, the CHA1 implies the commands. So it initiates an audio recording for a period of time, which is in this case 1 second, the sample period. And if the data is 00, then it will record, for example, using 196 kilohertz and 32 little Indian bits. They are the command 1, and thus creating the green spectrum. In the receiver end, the receiver create, look and see the green spectrum and say yes, it is command 1 used, and thus it is 00, and decode the information. As I talked earlier, we can say that each command is presented by these points, the harmonic and the peak point of the harmonic. So if we plot the 3D the 3D plot that we can see in figure 7, which is the Fourier transform of the commands used to send the 4 symbols, we can see clearly that the peak point colored here, for example, red one for the first command, red one for the first command, green one for the second command. They create a clear pattern. For better interpretability, we can project it on the frequency spectrum magnitude plane to have unique points. The first group is the first harmonic. The second group is the second harmonic. And from now on, we can use only the 2D plane to design the whole cover channel. So each harmonic of the clock, each harmonic of the carrier has its own projection, its own 2D projection. So to find the best 2D projection, we need to put a criterion. The criterion is that the best receiving frequency or the best attacking frequency is the frequency that helps the most in bit separation, in sample separation. So we can imagine to measure the distance between the red one and the purple one, and the biggest distance is the best one because it will separate the best those two samples. But however, if we take only the vertical distance, then we can have a case where the green one and the blue one are overlapped, which confines the receiver from sample 2 and 3. Thus, to make sure that we choose the right and the best frequency, we will use a pairwise distance. So for each group we say the pairwise distance and we do the variance. The peak of the variance means that the best separation means the least overlapping, which means the best frequency to do the attack. And this is the result in figure 10. To compare it to the traditional method, without knowing the SSAM equation that said that implies the harmonics, that the signal is located at harmonics of local oscillator frequency, we can use the brute force approach. The brute force approach is based on sweeping all the frequency in small windows. For example, here in 1 megahertz, and we can see we have the receiving frequency is 216 megahertz, and we can see that we have only two clear different colors for sample 1, sample 2, but 3 and 4 are almost overlapped, and we can say that the difference is due to noise. And thus, brute force emphasizes only that we can do a binary transmission. But however, in variance, we have the blue one, which is the first harmonic, and the second one, which is the second harmonic, and with the best separation, so we can say clearly that we can achieve 4 samples transmission. Thus, we reduce the research space for receiving frequency by a factor of 30. So after receiving the signal, the receiver discriminate or know the samples using a hierarchical principle. So it first determines the audio sampling rate, then the bit depth, and it reconstruct the combination, then so the command, and then it influences it to the sample value. So to know which audio sample and which audio depth, it uses the references, three references to be precise. The first reference is based on delta P, which is the absolute difference between the peak of the first harmonic and the peak of second harmonic. And we have an observation that if delta P is 0, it goes with the first sampling rate. If it is really greater than 0, it is for the second sampling rate. And the reference will be half the average. So why we use the average? We use the average as simple estimation, and I will explain it a little later. For the bit depth, we have P1 and P3. So why we added P3? Because we saw, for example, in figure 7, that P2 has a really close level, especially for sample 3 and sample 4. So we add an additional condition on P3, the third harmonic, to enhance the performances. And so we can decide the bit depth based on P3 or P4, because P2 and P3 are correlated. So we now at this point we receive the signal at the receiver frequency that we determined using the pairwise distance variance. We use a 1 megahertz receiving band, and we use a sampling frequency of 1.25 megahertz. We extract the three harmonics through time, change it through time, and we can see clearly the blue line, where we can see clearly the bits. But to denoise and reduce the noise, we use a moving average filter, and that gives the orange curve. After we have the orange curve, decide to estimate the samples values, we need to synchronize. Synchronization is done via differentiation or measuring the changes. So the first, we measure the difference between each two adjacent points, and after that, and we detect the really big difference to say it is the message started, the cover communication is started. And this we can see it by the first vertical line, and after that we computed the number of the points presenting one sample, which is represented by R sharp, as we can see the formula here. And after the first red line, we compute R sharp points, and we do the second line. And after the second line, we compute R sharp to give the third line. So between the first line and second line, we have one sample. Between the second line and third line, we have the second sample, and so on and so forth. So from the first line, so one sample is presented by R sharp point, R sharp value. We take the average of all these points to have one value to compare it to the references in slide number 10. Experimental results of our work, we tested our theory, our SSAM equation, and our attack on a Dell AudioGap desktop. We achieved a 2 bit per sample period, and sample period was 1 second, so we double the bit rate of a binary transmission. Secondly, we reduce the vulnerability attack frequency research, comparing to brutal force search, leveraging the SSAM equation or SSAM harmonic search by a factor of 30. We introduced a novel method to identify the reception frequency and the optimal receiving frequency using pairwise distance variance. And using CFDM encoding, we reduced the BOR, the bit error rate, to 25 to up to 25%. We can see from the left of the figure 14 that the distance, the BOR distance is less. The BOR versus distance, that the BOR is less than 10% when the distance is up to 28 centimeters approximately. And the gain, we can see clearly a high gain with an average up to 25%. As in conclusion, we said that oscillators or integrated oscillators in the system present a hardware vulnerability. So finding or searching the hardware vulnerability in the proximity of the oscillators is a good start. Secondly, we say that using SSAM model, frequency model, that the SSAM attacks are wideband, which means that we have theoretically an infinite number of harmonics that can carry information outside the air gap. And this make it really hard to defend against, because we need to isolate, or we need to do a cage or a Faraday cage to exfiltrate all possible harmonics. Also, using SSAM equation, we facilitate the signal investigation. Because we know the form and the form of the signal, the formation of the signal, and we know how we can use it to find the best sending frequency or attack frequency. And finally, the most important point is that leveraging SSAM model, we did not need to go to fine control the chip to achieve modulation, as the signal is created alone without any intervention of the attacker. And with using CFDM encoding method, we can leverage this auto modulation to set more than one bit per sample period. Thank you for all.